Hello, everyone, and welcome to your weekly webinar number 14 with me, your host, Michael Floyd. I'm your mentor and your mentee. You learn as much from me as I hope to learn from you. Now, starting with some of the things we need to cover. Still, the five of you have not filled out your introduction form. We are data scientists. We want to complete data sets, especially for Udacity, as much as possible. So hopefully meet with me sometime this next week. And besides, we're in a state of emergency for pretty much everyone who is behind right now, which is 12 of you. You have not completed either the third project or the second project, and many of you have not even completed the first project. I'm hoping we can get this ball rolling. If there are any questions, please ask me questions on Slack or through email. You have both. I was expecting a much higher graduation rate than what I'm going to see. It's unfortunate, but that is the way, I guess, the life works. Maybe not enough time. Maybe you pay again and you try again sometime. But don't ever give up on what you want to do as far as data science and analytics and machine learning and deep learning go. There will always be help. Udacity will always be here. So hopefully we keep seeing completions throughout this week and throughout the 28 days which you have been allotted for extra time. Uh, so with that being said, we have two that are on the third project, Wenji and Shan. I'm hoping they uh, help each other complete this third project. And congrats to Hannah for completing the third project. So Hannah joins Danny as the ones who are moving on to the second term for now. And like I said before, the money is already spent. Um, I usually say, a little in the morning, a little at night as far as time to spend on these lessons, but I would spend as much time as possible, just try to get this out the way as quickly as possible. So I could see a much higher rate of people going into the third term, second term, excuse me. And, just to keep everybody else notice, every time you spend on your lessons, just write it down on Slack to let your peers know, hey, I spent this much time on lessons and I've learned this and this and maybe had problems with this. And like I say every time, um, for the case of three different students, we have student A who has no responsibilities, and we have student B and C who both have jobs and responsibilities. But student B inconvenienced everybody else around them. Looks like Hannah and Danny are part of the student B category, and we're going to see if Wenji and Shan join um, Hannah and Danny as well. But all of you guys work and have families, but I understand sometimes you have to inconvenience them in order to get your goals accomplished, especially in the short term. All right. So with that being said, we have our 14th webinar coming to a close. I'm actually going to ask how many am I supposed to give, but this is actually the end of what is supposed to be the last topic, but it was to my discretion what it would be, and what I chose was reinforcement learning. Just something that I learned during my machine learning engineering nano degree that is not covered in this data science one. But reinforcement learning is different from what you would see with supervised. Where for supervised learning, we had a whole bunch of sklearn algorithms that use predictors to try to predict different labels, whether that be regression or classification. And we also had deep learning as well. We use that um, in this course as well. So we learned those two supervised learning algorithms and also unsupervised, right? So we did cluster analysis, we did dimension analysis, see if there are any possible ways to transform a better prepare the data for a subsequent analysis. So those are all covered unsupervised, as well as other topics as well that are not to my that I'm just not thinking about right now. But the way reinforcement learning differs from supervised and unsupervised is reinforcement learning takes what you would say is actions and penalties, more of a decision making. So reinforcement looks at a scenario or a state which you were currently in, and takes actions according to what it believes the best policy will be. And so that's what I'm going to show you now is uh, reinforcement learning, the algorithms, how it works, just to give you a quick glance over. And if we have time, I will try to run my project, which I did, which was training a smart cab uh, around a grid city to get to its destination. So um, I will also be talking about that project while I am going over the notes and algorithms that we will see. So with that being said, let me switch to my share screen. Okay, I am screen sharing. Okay, and yes, so this is the first thing I want to show you because part of a Markov decision process is very, very similar to what I will be attempting to explain as far as the reinforcement learning goes. So I will start off with Markov decision processes and the things that makes a uh, a example or a map a Markov decision process is that only the present state matters. So if you were given a sequence of states, like you went from state zero to state one to state two, and now you're trying to decide, being in state two, what action to take in state two. State zero and state one do not matter. In that regard, only the present state matters to find the optimal action. And it is stationary, meaning that the model stays the same. So, um, so this will be the uh, map we will use to post this example. So what we have is we have a starting place, and we have two places where the game can finish. It can finish up here with you getting a +1 for reaching the goal, or it can finish at -1 for you reaching. Maybe that's a negative goal. Maybe you fall off a cliff, so you just do -1. And what's really important in reinforcement learning are these rewards. So we delegate these rewards in order to make sure that um, the game learns in the fashion it wants. And of course, you could change the rewards, the amount that you set the rewards to, in order to perhaps reward or penalize uh, areas you do not want. So, example for a smart cab, if you do not want the cab to run into other cars, then if the cab runs into another car, then you penalize that a lot higher. So then of course, being 5 minutes late, right? So you make sure that first and foremost, not run into any cars. And, the extra 5 minutes it takes to be late will definitely be all right in regards to that. And so I went over states, I went over the model. So the model is directly related to the probability. So the probability of state S prime given you're in state S and you take action A. So we have an action space A. The smaller A is one action out of the whole action space. And so there are many actions we could take starting off. We can go up, we can go right. Um, in most games like this, if you go to the left, then you just end up at the square you were in. But of course, the model is um, the transition from to S prime, you know, um, given the state S and the action you take A. So the T is directly related to the probability in that regard. And the policy is the policy at state S would tell you, okay, so if you're at state S, then you're looking at all of the actions you could take. And given these actions you could take S prime, you want to know what is the best direction to move in order to what is the best direction to move in for the optimal policy. So that's what the policy S states. Given you're in a state S, we want to find what's most optimal at S. So what action to take given the state S. And the optimal policy is denoted by a star as a superscript for pi. Okay.
Is that the reward that I'm going to receive at every single.
And what I was saying, right? What I was going to say right here is when you see this, so you're still starting off as the same thing, but for now, what they have is they have a reward for each state is negative 0.4. So a problem you might have in a game such as this is, for one, if the car keeps traveling around and around and around without penalizing, then it will never have an incentive to reach its destination. Unlike if you reward each second it's late, of course, then it would have an incentive to reach its destination as quick as possible. But of course, you have to also keep in mind other penalties, like running over cars, stopping at stop signs or at red lights, right? These things need to be high enough in penalty so that the car definitely learns to regard these things as well. So right here, you have a reward set to negative 0.4. Also in the example that the videos give, if you were perhaps in state right here and you chose to move up this action, they provide an action of what you desire for probability of 0.8 and actions going at 90-degree angles to what you desire at probability of 0.1. So that's another way why you need a transition matrix, is because sometimes, although you take an action, you might not get the expected outcome you expect to see from taking that action. So having that probability, there can be different probabilities, although you take an action and you want to take action, but the action does not occur. So and so this is just an example. This would be a policy right here. So this is a policy. So given that you're in this state, you would choose to move up as far as the policy. Given that you're in this state, you would choose to move to the left. So this is a policy for the game. And so each state has its designated action to take if it's in that state. That's why it's called a policy. And for the reward that we have right here, this is the optimal policy for this reward. Of course, if you change the reward for moving toward a state to be higher and lower, perhaps some things might change. Uh, Perhaps to be cautious of going towards -1, it might try to run into the wall. We just place them in this state with probably 80%, but also move them to the left or right with a 10% probability for each, right? So to stay away from a -1 as much as possible. Let's say if we increase this to negative 1,000, right? Then it's definitely staying away from 1,000, because if you move up, you have a 10% probability of moving to the right. So that is the way in which you can change different penalties and rewards in order to affect the game.
All right, so having gone through that.
And infinite horizons. What that means,
reward that you see in those
just like I was saying before, is if you do not have a penalty that penalizes for just being stationary, then what happens is the game could go on to infinity. So you would not like that. And the utility is the other thing I was going to say is the utility of a state is the reward it gets for being in that state plus what it's expected to receive from the actions. So what this is saying is if you believe that the utility of being in state S0, then moving to S1, then S2, and so forth is greater than S0 to S1 prime and S2 prime and so forth, then utility of just being in state S1 and moving forward is greater than utility of being in state S1 prime and moving forward. And this is going to have to do with the algorithm, which I'm going to show you later. Okay?
You never get closer to the horizon.
Okay. And because of the infinite horizons and having the sum of all rewards having the possibility of going to infinity, what we want to do when we're looking to find the utility and we're looking at what can happen after the next state, after the next state, after the next state, what we would like to do is we would like to invoke a discount. We call this a discount. And a discount after it provides a value of less than 0, greater than or equal to 0 and less than 1 to the rewards that we get for going after the state which we're currently in. And of course, that makes this a geometric series. We're just taking the so we're creating a geometric series from the rewards we can get from each subsequent state. And so what that does, that allows us to compare two states compare to utilities, because if the rewards go to infinity, then both series are going to go to infinity. Whereas for this, the rewards, although they keep piling and keep adding up, they don't go to infinity. So we can find out and compare which utilities are better. And that's the point of the discount, is to be able to compare which utilities, which means that, overall, which actions will be better.
So now we got Bellman, and it turns out to be.
So this is just a review of some of the equations. What we have, we have the policy is the argmax, the best policy from what you would expect from the rewards starting at state ST, given the policy, given different policies that you could be invoking or using, right? So the optimal policy is the best policy that has the highest expectation given the rewards that are going from state 0 all the way to whatever state it finishes. And the utility, given the policy that you are looking at, or given the policy that you are providing or determining, is the expected value of the rewards given the state. And this is given the policy and the initial state being S. So that's how you know the utility of a state. So using the utility we know of the state, right? We can find the best policy by, given that we're at state S, we can take an action and be at state S prime with some probability and multiply that probability by the utility. We want to find the best action that would give us the highest probability times utility. And that would be the best policy. And yeah, so this is just writing it out, the utility function. Let me play this. So
In some sense, the key.
Okay, so what we have is we have the discount rate. So this is for the utility for just S. So we have the reward we got for landing on S. Then we discount what we expect to see. We discount the best action that we expect to take multiplied by the utility of S prime, which is the state we expect to be in given that action. And of course, the utility of S prime would just be the same thing, reward, which is discounted, then plus the discount of the discount, which we just did. So that's how you can see that it does go into a geometric series.
So I'm going to update the utility.
Okay. And in order to find the utility, the value iteration formula that happens is, so you start off with just arbitrary utility values, and so you have arbitrary values. So you have a reward for being in that state, and then since you have utility values, you could then take an action to land you in the best utility value. And given that you landed in that action, you then now have a reward and that reward can be passed on. Well, that would be the reward for S prime. And that S prime will then reward be passed on to the next iteration of utilities at t+1. And then so at t+1, you not only have the reward as you received in um, uh, the reward and action you saw at utility at the first step, but you also have the reward you see from the second step. So it's more like more truth that has been passed on. So if you can imagine, let's say you have arbitrary utility values, and these values, let's say they start at S0, S1, S2, S3, and go on and so forth, which you just created them. So when you keep updating your utilities, what you're doing is you're pushing what you had as far as S0, 1, 2, 3 back. So now you have a new S0, then you repeat this, you have a new S0, so now this is S1, and it repeats this and repeats this and repeats this. And remember, we're discounting what we find as far as utilities. So if we continue to discount, then what we have seen and what we have set as arbitrary values becomes smaller and smaller and smaller. And what we have gotten as far as our actual rewards will then be great enough in order for it to converge, because it will converge, and then we will uh, have our we'll have our actual utility, and with the actual utility, we will have the optimal policy that we should take given any state, or the optimal policy. So we should know what action to take given any state. That is all on the Markov, and now I'll be talking about uh, reinforcement learning.
Reinforcement learning.
So, reinforcement learning. So, pretty much what you are given is the state you are in, the actions you can take, the rewards you get after uh, making those actions, and the S prime, which is the new state which you're in. And from this little transition, what you are going to then have is you're going to have a learner that then finds the best policy. Okay. And these are a whole bunch of different types of models that can be used, and some of them are actually be used in combination. So um, for reinforcement, you will have transitions. So it won't be just a transition and then a learner, then policy. You will have transitions, and you will create a model from those transitions. And from that model, you will you will have a simulator. Well, in the project, what we had is we had a simulator that simulated the transitions, and from all those simulations, um, then learn the policy. So what you can see from the project was model, then simulator, then transitions. Then from transitions, have a learner, then policy.
All right, Charles. So what would you call approach back end?
So these are just names they gave to this, right? What I said before, right? Model, simulator, have the transitions, then the learner, then the policy, reinforcement learning based planner, and the model based reinforcement learner is to go from transitions to a model, and from the model to the policy.
All right, we're going to. And the usage is not so.
So it's just another graph to make what I was trying to provide, make it look a little better if it makes more sense. So what you have is you have states and in action coming in, and you will have coming into the transition and reward matrix, and then you have S prime, the new state, and the reward from that state, and you will use it to solve the Bellman equations, or the equations that we went over previously with the policy and utility. And this U is the utility. So given the state you were in, this transition will update this utility, and this utility will therefore update the policy. So I mean, in the policy, of course, we are using the policy directly to determine the action, but we are indirectly learning the policy because we're going from the transition to the utility, then to the policy. So that's why they call this, we're directly using the policy, but we're indirectly learning it. And here, the transition, we directly learning because the action is coming from here, and indirect use because what we are doing with the transition is coming from the policy. And so this is using Q. I was waiting for it to load, but it's not really important. So this is a way we're going to do this as far as going from the transition to the utility to the policy is using Q, which Q is similar to utility, and that now we're taking the maximum Q, which is the maximum S prime given A prime, or the state that we are going to be in, the action we're going to take from the state that we're going to be in. So Q of S of A, so that is the state that we're in and action we have took. That is equal to the reward that we get for being in this state, plus, of course, we're adding in our discount and the transition matrix going from state S to state A, and then being in S prime, and then the maximum Q, which we would find from going from maximum Q we will find for being in this state S and going to take action A prime, which A prime, of course, is dependent on our policy. And so now, how do we estimate Q?
That you see.
Good.
Okay. So the way we estimate Q is we use a learning rate. So you are not provided with Q, but you arbitrarily set values for Q, and you use a learning rate to update those values for Q. So the learning rate, so this alpha over the left arrow is a function. And so that function, let's look at this, is the 1 minus the alpha times v plus alpha times x, which is your response that you were getting from the algorithm. And so what you are learning, as fast as the higher this gets to 1, you are learning and leaving behind what you have thought to be not what you had assumed previously. And so you have R, which is the reward you got currently. You have your discount rate, and you have the maximum Q hat, which Q hat is the utility of the next state. So the next state, of course, is going to be affected by the policy. And the policy being in an S prime is going to tell them to move at A prime.
Yeah.
This is just the convergence algorithm. And the learning rate requires that the expected value, the sum of the learning rate, will sum to infinity, and also expects that the sum of the squares of the learning rate is less than infinity. One value that they commonly use is 1 over t, which t is the time. So the time, of course, 1 over t is not a converging as far as it goes to infinity, but 1 over t squared is converging. And like I said before, the Q starts anywhere, and you have the reward for being in this state. You take an action, and you have a discount rate, and the S prime, and then based on the action you take and the state you're landing in, now you're going to then take another action, which is A prime. This is the utility of the next state. And then, so if you keep doing this, then your estimate of Q hat, because you're learning as you go, if you keep doing this, then your estimate of Q hat will go closer to, will move towards Q, will converge to Q. If each state in each action is visited infinitely often, or as often as possible, or as often as necessary. So each state in each action needs to be visited, of course, at least once. Most likely, you'd want to visit it, even if most likely you could be uncertain that given that you're at a state the action that you take is the most optimal. So you want an algorithm in order to make sure that you're not at a local minimum as far as being in state S and just only taking action, let's say action 0. So one thing about how to choose action, I think I'm going over to the next slide.
I think that is a clever idea. Random research. That was one of the ways that we got. Yet most of the time we're.
Okay, yeah. I was going to the next slide. So for choosing actions and how to choose actions, they give us a couple of choices here. So if you always choose the let's say one action, A0, you won't learn anything because you're always choosing the same action. If you choose randomly, then you will never use what you know to be correct from the utilities that you're constantly getting from updating this algorithm with your learning. And if you use what you've learned, there's a possibility that you will be in a local optimal place and not the exact optimal location. And random restarts will be way too slow, as in just continuously restarting the algorithm and trying to learn. If you had infinite time with a number of simulators, then that is, of course, feasible given the size of the project that you're on. But most people don't have an infinite time and a great number of simulators. So what we're trying to avoid is going into a local minimum. And so what is suggested is, um, you've learned a policy which will tell you the correct action to take, but you only take that action with probability. Let me see if I can get this hand out of the way.
We're spending, assuming
Okay, you only take this action with probability 1 minus epsilon, and you take a random action otherwise with probability epsilon. So although you continuously learn and continuously learn and continuously learn, there's still a chance that you will take some random action. And based on the chance of taking that random action, then if you have an infinite number of actions you take, then you will visit every state. And the algorithm would therefore have more confidence that you have the optimum policy. And we call this epsilon the exploration fraction. So, and also for, okay.
All right, so let's say something that we actually know about this approach in reinforcement learning theory called the explore.
So epsilon, we call it pre-limit infinite exploration, is epsilon can just decay over time. So you don't have to, let's say if you choose epsilon initially at maybe 0.3 or so, that epsilon can decay and decay and decay until, you do have a chance of moving towards something that is not an action that is not optimal to your policy. But once you hit that optimal policy and you hit enough iterations, it should make more sense to not need the epsilon to be as high. Okay, and so with that being said, we have 15 minutes left. What I'm going to do is I'm going to run my project. I'm not sure how to get the simulator working, which is unfortunate. Let me see. Might be able to try. Okay. Hopefully, okay, I did not do it. Yes, I don't know how to get the simulator working, but so what this environment had is what you can see right here. So you have a smart cab. So the project was a smart cab, and the smart cab had a deadline. So you started off with, I'm not sure how many moves was possible for you to make before your time ran out. But of course, you're trying to get to the right spot before the time runs out. And you have a whole bunch of different inputs. So, given you're at a certain point on the grid, so this is a grid that a car is driving on. So, given that you're at a certain point on the grid, you're looking at whether the light is green, whether there's oncoming traffic. The next point, I believe um, that is the action you want to take. You if there's a car to the left of you, remember, because if there's a car to the left, then you cannot make a right turn if a car is coming from the left, and oncoming is if you are trying to make a left turn, you have cars that are oncoming, you can't make that left turn. So both of these matter, and the action you don't take is right, and the reward is, or that you receive, that you see here, the reward is 12. So I rewarded 12 whenever it reached its destination. I will run this. So what you see here is that, did not succeed the first time. It succeeded the second time, third, fourth, fifth. It succeeded 98 times. So I'm not sure which one it didn't succeed in. Yeah, somewhere down the line here, it actually did not succeed, which is surprising that the algorithm. Okay, maybe it's somewhere in the beginning. I can't find exactly where it failed, but wait, yeah. So I can't find exactly the second spot where it failed, but it failed twice to my observation. It says number of successes is 98. I don't see what number is skipped. That's not important. So I'm going to run the simulator and show you what happens. So this is pretty much it running. The car either passes or fails. So it's going to keep running and telling exactly the lights and the traffic that are oncoming, and it's going to take actions based on the state that it's in. In the state are all those variables that you saw, right? The light being green, where you are in reference to the actual destination. That's something that I actually not put on there is, where you are in respect to the destination. So where you are to the left or to the right of the destination, that is also a part of the state, as well as the light, the oncoming traffic, all of these things. So as you can see, the algorithm learns pretty quickly. So after the first try, it learns exactly how to get about to the correct destination relatively fast. So you doing simulations, even if you had more states and it took you more simulations, given the epsilon and exploring each possible action given the state, it will rather quickly find the optimal policy. So that's what this is doing right here. I just used 100 simulations, and this one, just had 71 successes, but I mean that's still pretty good as far as success rates. This one has 71 successes. As you see it, it went over. It skipping after the first couple. It didn't do number 100, which is surprising that we had a failure at that level. But yeah, you see some in the 80s as well that are failing. So this one, maybe the epsilon or just the actions that we took were not as good randomly. So of course, we use more than 100 simulations. If we use 1,000 or 10,000 or 100,000, remember it must go to infinity as far as the number of times you do this in order to see an exact convergence to the most optimal policy. So this one is converging a little slowly, but um, yes. So this was the project. There was a simulator that would show like a grid. You have a cab, and a cab, you see the cab moving. You see other cars as far as traffic, and the cab will obey the lights, whether it's red or green or blue, whether the cars are oncoming or whatnot, and then it will reach its destination. It was pretty cool to see, and I was wishing to get the simulator up, but I could not. And I'm going to stop it right there. All right. So if there are any questions about reinforcement learning or any questions about the 3 projects, just let me know, and I'll be waiting for the next 7 minutes or 5 minutes. All right. I'll post them on the group chat here. If I don't see them on the group chat, then post them on the Slack channel. I'll be looking at both. Also, if everybody could meet with me sometime this week, tomorrow, set a meeting, that will be great. I'm looking forward to seeing everybody's progress, or at least the best progression of themselves at this point. So you don't have too much time. Set up the meeting, and I will be sure to be there as well as answer any last minute questions on Slack. Try to get everybody on board in completing the projects. I think I heard a question. Is there a question? No, I don't see a. Okay, I thought I heard the direct message. No, I do not see a question. All right, looks like there's no questions. I'd like to thank everybody for watching. If you were watching, hopefully we get the ball rolling and many people finish the first semester so they can move on to the second semester. All right. With that being said, I am out.